Okay, so we want to talk about integration by substitution from calculus, and in particular with definite integrals, integrals that have bounds. So let's consider the following. We're going to solve this in two ways. So we've got the integral from 0 to pi over 4 of secant squared of theta times the tangent of theta d theta. Okay, so for method 1, we want to sort of recall the following. So recall the derivative of secant of x is equal to secant of x times the tangent of x. That's actually pretty helpful because we can take this and rewrite this. So again, in method 1, we're going to rewrite this, sort of inspired by this. So this is going to be secant of theta times secant of theta tangent of theta d theta. So I'm going to have this sort of u du situation going on here. So we're going to let u equal secant of theta. Now the derivative du is exactly secant of theta times tangent of theta. And that's very helpful. D theta. So that means that this is going to be du. This is going to be u. But remember, we need new bounds. We're switching variables. We're going from variable theta. These are theta bounds. And we're going to variable u, so we need corresponding u bounds. So don't forget this. So I need a new lower bound and a new upper bound. To find those, we just use the substitution statement. So my lower bound is u equals, well, theta goes in for theta here. So this is secant of 0. Well, if that bothers you, just think about the definition. You can always think about that as 1 over cosine of 0. Well, that's 1, right? Cosine of 0 is 1. So this must be 1. Well, I need a new upper bound as well. So this is u equals the secant of pi over 4. But this is exactly the square root of 2. To find this, it's helpful to know the following triangle. This triangle comes from half of a square. If you take half of a square, you'll find exactly this triangle. So you can say both of those sides are length 1. This is radical 2. This diagonal will bisect the angles or chop them in half. So that's pi over 4, and that's pi over 4. And when we say secant in math, this is just the reciprocal or the flip of cosine. So you can mentally just take the cosine and flip it. Cosine would be 1 over radical 2. Flip it for radical 2. So my new lower bound is 1. My new upper bound is radical 2. Now this is exactly what we're calling u. And this is exactly what we're calling du. Well, this is nice because we can use the power rule. So this is u squared over 2. We want to evaluate that from u equals 1 to u equals radical 2. Notice when I'm careful to change my bounds, I don't go back to variable theta. All the info that I need is encoded in the bounds. So it's almost like once I get to this point, I forget everything that happened before it because everything is encoded again in the bounds. So that's going to give me the square root of 2 squared over 2 minus 1 squared over 2. And let's see what we get here. So this is going to be radical 2 squared, so that's going to be 2 over 2, so that's 1. That's going to be minus a half, so it looks like I get exactly 1/2 as the value of my integral. Now for this integral, we mentioned before we can actually solve it in two ways. Let's go ahead and solve this the other way now. So this would be method 2 for the same problem. Okay, so we're going to start with the same problem. So I'll say method 2. So we still have the integral from 0 to pi over 4 of secant squared of theta times the tangent of theta d theta. Now, for method 2, we need to recall something a little different. We need to recall the derivative of tangent. Well, the derivative of tangent of x is exactly secant squared of x. That's going to inspire my substitution this time. So this time, I want to try to let u equal the tangent of theta. Well, the derivative du is exactly secant squared of theta d theta. So that's helpful because this gets rid of this. And we mentioned before we're changing variables, so let's go ahead and change the bounds. We need new bounds. These sort of expire in a sense. They're only good for thetas. We want corresponding bounds for u's. So to find my new bounds, I'm going to take the lower bound of theta equals 0 and just plug it in for theta. So u is equal to the tangent of 0, but we know that the tangent of 0 is exactly 0. For my upper bound, I'm going to plug pi over 4 in to tangent. And tangent of pi over 4 is 1. Again, you can get that by looking at the same triangle we mentioned before and just computing the tangent. So we've got 1, 1, radical 2. That's pi over 4, and that's pi over 4. And you can clearly see, right, if I take the tangent of this, opposite over adjacent gives me 1. So that means in method 2, I'm integrating from 0 to 1. I'm going to have, let's see here, this looks like u, and this is du. Right, that's u, that's du. That's not terribly bad to compute, so that's just going to be u squared over 2 from 0 to 1. That's exactly 1 squared over 2 minus 0 squared over 2. And again, that's exactly 1/2. So kind of a neat one. Okay, so let's go ahead and talk about another example. So here comes another definite integral where we want to use integration by substitution. Now, if this one seems a bit strange for you at first, that's okay. We can actually just take it and rewrite it, do a little algebra. So we can rewrite this as e to the 1 over x times 1 over x squared dx. Again, so that idea that if I'm dividing by something, I can think about it as just multiplying by the reciprocal. And let's try a substitution. Seems to be a lot going on here. Well, let's try the innermost function and see if that gets us somewhere. So this is what I mean by innermost function. If I think about the composition of e to the x with 1 over x, this is the inside function. So u is equal to 1 over x. I know in the next step we need to take a derivative, so we should probably rewrite this. So let's go ahead and take the derivative. That's going to be minus x to the minus 2 dx. And we can multiply both sides by minus 1 to get this by itself. And if I rewrite that, I get exactly this. And you can see that's helpful because this quantity can be replaced by this. So that seems nice. And we're switching variables, so we're going to need new bounds. So let's get a lower bound and an upper bound. So remember how to get those. You're going to take your old lower bound and plug it into the substitution statement here. So I plug 1 in for x, and I get 1. So that wasn't changed. Now for the upper bound, I'm going to plug 2 in for x. If I plug 2 in for x, that should give me a half. So I'm integrating from 1 to 1/2. Let's see here. So this quantity right here, that's this. We're going to call that -1 du. We're going to write it like that. And this is exactly e to the u. Now it might seem a little awkward that we're integrating from 1 to 1/2, but remember there's a theorem from Calc 1 that says that we can reverse the order and that'll negate the integral. So if I flip the integral, it negates, that becomes positive, and then I get the typical orientation from left to right. Okay, so this doesn't seem so bad, right? So we know the antiderivative of e to the u is itself. So let's see here, that's exactly e to the u. We're going to evaluate from 1/2 to 1. And so that gives me e to the 1 minus e to the 1/2. But that's exactly e minus the square root of e. And that's the exact value of our definite integral. Okay, so let's go ahead and try another one. Let's say we've got the definite integral from 0 to the square root of pi of t times the cosine of t squared times the sine of t squared dt. So this looks pretty involved. Well, let's make an initial substitution. So I know that t squared and t are pretty closely related by a derivative. So let's let u equal t squared. Now if I take the derivative of that, so du, that's going to give me 2t dt. Let's go ahead and divide out the 2 because we want to get rid of this t dt business right here. And then we want some new bounds, right? Every time we switch variables, we want to get corresponding new bounds. Okay, so remember t goes in for t here, and that's going to kick out a u bound. So it's going to be 0 squared, so it looks like 0. And then for our new upper bound, so this t value goes in for t here, and that's going to give us a u bound. So we're going to be integrating from 0 to pi. So this right here gets replaced with 1/2 du. Our new bounds, we're integrating from 0 to pi from here. And this is going to be the cosine of u times the sine of u. Okay, so I know that sine and cosine are related by a derivative. So we can actually make a second substitution here. So let's go ahead and let w equal the sine of u. Notice I pick a new substitution variable. That's not to confuse this u. Now when we take the derivative, du is exactly cosine of u times du. And again, we're going to need some new bounds. So new bounds. So my lower is w equals, well, u goes in for u, sine of 0, but we know sine of 0 is 0. And my upper is w equals the sine of pi. But that's also 0. And we know any integral from a to a, the same value to the same value, must equal 0. So I don't even need to calculate this. That's a theorem from Calc 1, this is exactly equal to 0.